Hello everyone. So in this lesson, we're going to talk about functions and what we call average rate of change. So when you see average rate of change, we're most likely going to abbreviate it as AROC. So if you ever just see AROC written, it's just the acronym for average rate of change. So just kind of diving right in, so we're going to first talk about what it means to be a function. So a function, as it is written, is a mathematical relation that maps a set of input values to a set of output values such that each input value is mapped to exactly one output value. A very fancy way of saying it's going to pass the vertical line test, there's no repeating x values, etc., etc. So components of your function, we're going to have what we call the domain and range. So the domain and range are going to be represented by the x and y variables respectively. So your domain is going to represent the set of all x values, the range is going to represent the set of all y values. Now kind of transitioning into average rate of change. With average rate of change, we're actually going to be finding what we call the slope. So with the slope, you guys have been doing that practically since you could walk. So we're going to be finding the average rate of change or even the slope between two specific points. So just kind of starting off, we're going to find the average rate of change of either linear and or nonlinear functions. So we're going to start off with this nonlinear function. We're going to start off with this cubic function. So we have f of x equals negative x cubed plus 3x on the interval from -2 to -1. So what you're going to do is we're going to be taking our values from the interval and we're going to be plugging it into your function for that variable. So for example, I want to take f of -2. So we're going to do negative of -2 cubed plus 3 times -2, and we're going to evaluate this part. So negative of -2 cubed is going to give you a positive 8, and then 3 times -2, which is going to be -6, and then when you evaluate, we get 2. So next, we're going to evaluate -1. So I'm going to do f of -1, so that's going to be negative of -1 cubed plus 3 times -2. So when you do this, so negative of -1 cubed, so -1 cubed is going to give you -1, a negative of a negative is going to give you positive. So we're going to have 1 minus, that should not be a -2. Whoops. There we go. So 3 times -1. I knew something looked weird. So that's going to be 1 minus 3, which is going to be equal to -2. So now that we evaluated both of those parts on the interval, now we're going to evaluate and find the average rate of change. So your average rate of change, so your AROC, we're going to use these specific interval values to plug in. So I want to do f of -1 minus f of -2, and then that's going to be over the input values. So we're going to have the output values, which are the y values, over the x values. So when I plug in, so the output of -1, which as you can see is -2. So -2 minus the output at -2, which is +2. And that's going to be over -1 minus -2, which is going to turn into -1 plus 2. Let's shorten this a bit. So now we can simplify. So -2 minus 2, which is -4, over -1 plus 2, which is 1. So we're going to get an average rate of change of -4. So now looking over here at number 2. So same idea, we're going to evaluate your function at these specific interval values. So I want to make sure that I'm using the correct notation. So because we're using h of x, that means when I write it out, I need to use h of that value. So I'm going to plug in 1. So we're going to have 1 plus 1 over 1 plus 6, which that's going to give you 2/7. And then we're going to plug in 4. So h of 4. So that will be 4 plus 1 over 4 plus 6, which that will give you 5 over 10, which simplifies to 1/2. So now that I have both of my output values, now I'm ready to do the average rate of change. So my average rate of change So once again, make sure you're using correct notation. So I'm going to do h of 4 minus h of 1. That's going to be over 4 minus 1. So when I plug in, so the output at 4 is going to be 1/2. And then we're going to subtract the output at 1, which is 2/7. And that's going to be over 4 minus 1, which is just 3. So in order to subtract the fractions in the numerator, I need to get a common denominator. So between 2 and 7, I need to get a common denominator. So when I multiply them together, I get 14. So that's going to be my new denominator. So my new numerators, so 2 to get to 14 times 7, so 1 times 7, which is going to give you 7. And then 7 times something, which gives you 14, which is times 2. So 2 times 2, which is going to give you 4. And that's going to be all over 3. So now that we have a common denominator, now I can subtract. So in the numerator, 7 minus 4 is going to give you 3. So 3 over 14, all over 3. And then I'm going to rewrite this as 3 over 14 times 1/3. And then what's going to happen, your 3's are going to simplify, which means all we have left is 1 over 14. So that would be your average rate of change. All right, so now that we did a couple algebraically, now we're going to look at a graph. So with a graph, luckily, because it's essentially the same idea as slope, you're going to just do your rise over run. So from here, I'm going to find the output value at -1, which is going to happen right here at 0, and then my output value at 3, which is going to be up here at 4. And then what you can do is just your rise over run. So when I count and do rise over run, so 1, 2, 3, 4, so I did a rise of 4, and then 1, 2, 3, 4, a run of 4, which means for your AROC, it was 4 over 4, which means we're just going to have an average rate of change of 1. So then if you come across a piecewise function, what's going to have to happen is you're going to look at your interval, and you need to look to see where those values are going to fall in your interval for your piecewise. So if I want to evaluate -2, well, -2 is less than 1, so that means I'm going to use 3x minus 2 to evaluate -2. And then if I want to evaluate 3, well, 3 is bigger than 1, which means I need to use x squared plus 1 to evaluate 3. So to give you an idea, so checking my letter, so we're going to use f. So I want f of -2. So we're going to do 3 times -2 minus 2. So that's going to give you -6 minus 2, which is going to be equal to -8. Now I want to evaluate what's going to happen at 3. So f of 3. So I'm going to do the x squared plus 1. So that's going to be 3 squared plus 1, which that's just 9 plus 1, which is equal to 10. So same idea, now that we have our outputs, now we're going to do average rate of change. So I need to do f of 3 minus f of -2, and that's going to be over the difference of the inputs. So your output at 3, which is going to be equal to 10. So 10 minus the input at -2, which is -8. And that's going to be over 3 minus -2. So 3 minus -2 is going to turn into 3 plus 2. And then same idea in the numerator. So we're going to have 10 plus 8 over 3 plus 2, which is 5. And then that's going to simplify and give us 18 over 5, which that does not simplify. So that kind of gives you an idea of average rate of change in multiple different representations. So number 5 is just kind of more practice. It's just doing average rate of change, but over different intervals. So for sake of time, I'm going to skip that one. So now we're going to look at our functions. We're going to look at behavior of functions. So I know you guys have seen this before. Hopefully this will just be kind of a recap. So with increasing and decreasing, we're just looking at the value of the slope. So if your slope is positive, what that tells you is that your function should be increasing. Whereas if your slope is negative, that means your function should be decreasing. But more specifically, we can also look to see whether your function is positive or negative. So in order to distinguish this, you're going to look at your roots. So the root on to positive infinity, it would be positive. And then from negative infinity all the way to whatever your root is here, that would be negative. And then same idea over with decreasing. So now we're going to look over at concavity. So with concavity, this is looking at the slope of the equation at specific points. So that's what we refer to as the average rate of change. So as you can see, what I have in orange, those orange arrows or lines, that is taking the slope at specific points. So as you can see, the slope starts off over here strongly negative, but as we follow this curve, it's going to flatten out and get closer to 0. And then once it gets to 0, then it's actually going to start getting more positive, and it's going to get stronger and stronger as a positive value. And what that tells you is that the average rate of change of the slope is actually increasing. And when the average rate of change is increasing, that tells you your function is going to be concave up. So you guys might know it as like a happy face or whatever. And then kind of the same similar idea for concave down. When I look at this parabola here, I start looking at the slope of my parabola and notice how it's actually going to start kind of flattening out and getting closer and closer to 0. And then once it hits 0, then now my slope is going to become negative, and it's actually going to get steeper and steeper, which means it's going to get more and more negative. So what that means is your slope is decreasing, which means your average rate of change is decreasing. When your average rate of change is decreasing, that means your function will be what we call concave down. So we're going to use these attributes to help us fill out this next section. So I give you a sample graph. It has a linear and then some nonlinear components. And then we want to determine the following intervals, whether it's increasing, decreasing, concave up, concave down, and then both increasing, concave down, so on and so on and so on. So the first thing I actually want to talk about is what we call a point of inflection. So a point of inflection is what I refer to as just a POI. Is going to indicate where a concavity of your function is going to change. Now, the number of POIs is also significant because you need to know how many POIs you can have. So the number of POIs you can have is going to be the number of extrema, which is the number of minimums and maximums, minus 1. So if I have 3 extrema, 3 mins and maxes total, then that means I would have 2 points of inflection. If I have 5 extrema, that means I'd have 4 points of inflection. So to kind of illustrate this, I drew a couple graphs down here, just to kind of give you an idea. So for example, if I have 3 total extrema, that means I'm going to have 2 POIs. So over here, on this first graph, I would be concave up from negative infinity until that point of inflection, and on the interval from this POI to positive infinity. So those POIs are what's going to separate the concavity. And then if you look from this POI to the next POI, that is where we're going to be concave down. And then it kind of went crazy down here. So just kind of giving you an idea that there's no minimum or maximum number of extrema or POIs that we can have. All right, so now looking at this part right here, looking at the graph, we're going to look to see where it's increasing. We don't care whether it's positive or negative, just where it's increasing. So meaning, where essentially do we have a positive slope? So if I look to start off on this linear segment, well, that's going down. That's a negative slope, which means it's decreasing. But then we have this nonlinear part that's going to be going up. So that part would be increasing. And then we also have another increasing part from 4 to 7. So we're going to represent both of those intervals using our interval notation. So I know I'm going to start off, that's decreasing. So we're going to go from, is it -2 to 0. And then I have another interval, which was 4 to 7. So when you have multiple intervals like this and you want to connect them, we're going to use a symbol called a union, which is like a capital U. So it's like a chain link. So now we're going to look for decreasing. So I'm going to get rid of this, start fresh. So for decreasing, we're looking to see where the slope is negative. So I know from here to here, the starting, and then we're also going to be decreasing on this entire interval here. So that tells me I'm going to be decreasing from -4 to -2 and 0 to 4. So decreasing from -4 to -2 with a union, since we have multiple intervals, then 0 to 4. So the next part, we're going to be looking at concavity. So with concavity, we're looking to see where the average rate of change is increasing. So one thing to know is in order to look at the intervals for concavity, you have to use the points of inflection. And the concavity only refers to nonlinear segments. So when we're looking at concavity, we're not even going to consider this linear part over here. We're only going to look at these nonlinear parts. So for concave up, we have a point of inflection right here at 2, which means we're looking to see where the slope is going to be increasing. So that is going to happen on this part right here. So that means we're looking from 2 to 7. And then same idea, but now we're looking for concave down. So where your graph is going to have an average rate of change that's decreasing. So that is going to be from -2 all the way to 2. So now we're going to get a little bit more specific. So now we want where it's both increasing and concave down. So if I want specifically where it's concave down, that's just going to be this interval right here from -2 to +2. But then I want where specifically it's increasing. So increasing would be just this first part right here. So from -2 to 0. And next, now we want both decreasing and concave up. So I'm going to get rid of this part. So concave up is going to be this full interval right here from 2 to 7. But then I just want where it's decreasing. So decreasing where it's going to be going down, which means I just want this part. So from 2 to 4. All right, and then down here, now we want to know where it's going to be positive and then negative. So I'm going to go ahead and clear the graph. So in order to use these values, or find these values, we're going to use the roots. That's terrible, but same idea. So we're going to be using our x-intercepts, which you guys know them as roots. They may also be known as zeros, or in some situations we call them solutions. So there's a bunch of different potential names that we could use for these. So if I look at my graph, we have 2 roots. So it would be here at about 2.5. And then over here, which is about 5.5. We're going to be much more descriptive and specific on any assessment where either we give you the roots or we're going to give you a way in which you can solve for them. So for positive, we're looking where it's above the x-axis. So above the x-axis would be the entire function as it starts until we get to 2.5. But then it's going to pick right back up 5.5 to 7. So the only part where we're negative is going to be just this little part right here. So I'm going to represent that using interval notation. So positive would be from -4 to 2.5. And then we have another interval, which is going to happen from the other root, which is 5.5, to 7. And then for negative, we're going to use root to root, so 2.5 to 5.5. Ta-da! All right, moving on. So I have a love-hate relationship with problems like number 7. So this is just drawing a graph given a written description. So starting off, so the graph of k is increasing on the intervals from -4, 1 and 5, 7. So what I like to do is I actually will go to my graphs and I will do these little graphics. So from here, so from -4 to +1. So I know this is going to be increasing. And then I also know it's going to be increasing from 5 to 7. So write that out. Okay, and then it's going to be decreasing on the interval from 1 to 5. So I'm going to do this with another color. So decreasing. Additionally, the graph of k is going to be concave up on the interval from 3 to 6. So then I'm going to do another layer. So from 3 to 6. So we're going to be concave up. And then concave down on the interval -4, 3, and 6, 7. So essentially the other side. So we're going to be concave down and concave down. All right, so before I actually start drawing the graph, there's a few details that I want you to kind of keep in mind. So we're going to start with just the increasing versus decreasing. So whenever your graph is going to change direction, what that tells you is we're going to have an extrema. Now, when I say extrema, that means we're going to have either a minimum or a maximum. So if I'm going from increasing to decreasing, that means we would have a maximum. Whereas if I go from decreasing to increasing, that means we're going to have a minimum. And then next, we're going to look at a change in concavity. So if you change concavity, then what's going to happen is you're going to have a point of inflection. So what that's going to look like, so let's start with the extrema. So I'm going to have increasing to decreasing, which means I'm going to have a maximum at 5. And then when I go from decreasing to increasing, that means I'm going to have a minimum over here at 5. Whoops, this is the next value of 1, but a maximum of 5. And then a minimum at next value of 5, but the minimum value I'm saying is 0. So notice how we don't say it has to be positive or negative. So there's a bunch of different possibilities for this graph. All right, now let's go ahead and do our our points of inflection. So we're going to have a point of inflection at 3, where the concavity is going to change. So a point of inflection is going to be between the minimum and maximum. It can't be above a max and below a min. So that means we're going to have a couple points of inflection at both 3 and 6. So the y values don't necessarily matter. So here, I'll even do this just to kind of mix it up a bit. All right, now that I have those points, now I'm ready to draw my graph. So it has to start at an x value of -4, and then it has to be increasing until I get to an x value of 1. But it is concave down, so I need to draw it kind of like a sad face. Well, we're doing math, so that's already sad. Just kidding. So from -4 to 1, So kind of concave down. So that's the first part. Now we're going to be decreasing but still concave down until we get to the point of inflection. So decreasing but concave down until we get to the point of inflection. That point of inflection now tells us we're going to be concave up. We can do this better. There we go. To our minimum. And then it's going to be increasing until we get to our point of inflection. We're still increasing, but now we're going to change concavity. So now it's going to be something like this. Ta-da! So there's one of your possibilities for your graph. Now next we're going to look at some attributes of these graphs. So this is the really important page. This is what AP can probably throw at you in terms of descriptions, but we'll go through it. So looking at number 8, so the function f is defined on the interval from negative infinity to positive infinity. And then the point P has an x-coordinate of P, the point Q has an x-coordinate of Q, and the point R has an x-coordinate of R. So just a very fancy way of saying when we are labeling these points, we're just going to use P, Q, and R. Now keep in mind, well, we should have done a little bit better on this. These should have arrows, which means this is going to go on to negative infinity. And then over here on the right side, this will also go on to positive infinity. Now that's in terms of the x values. Now the y values also, but the x values are really what's important. So we're looking to see where we have a local or relative maximum. So you can call it either local or relative. It doesn't really matter. They're kind of interchangeable in that aspect. So we're looking for a maximum, which means we're looking for where it changes directions from increasing to decreasing. So that's going to happen right here at point P. So point P is going to be our relative max. And then your relative min is going to be when it changes directions from decreasing to increasing, which is going to happen at point R. And then we're going to have an inflection point where the concavity changes. That's going to be between, which means we're looking at point Q. So now we're looking for where it's increasing. So my function is going to be increasing from negative infinity all the way until P, but also from R to infinity. So we have a couple intervals on this one. So you're going to write it out as negative infinity to P, and then union, then R to infinity. Next, now we're looking for where it's decreasing. So that's going to be from P to R. So that's that first section. So now we're looking at the average rate of change. So with the average rate of change, we're looking to see the concavity. So more specifically, if I say it's increasing, we're saying that the concavity would be concave up. If I say it's decreasing, that means we're saying it's concave down. So we're going to look at the specific intervals. So from negative infinity to P, we're looking from here to here. So because the average rate of change is going to be flattening out, which means the average rate of change is going to be decreasing. So we are concave down. Because we're concave down, that tells us that it is decreasing. And then the average rate of change on the interval from P to Q, well, we're still concave down, which tells us that the average rate of change is decreasing. And then the interval from Q to R, well, now on this interval, we're now concave up. So that tells us that your average rate of change is increasing. And then on the interval from R to infinity, so that's going to be this last interval over here. So we are concave up, which tells us that the average rate of change is increasing. So now we're going to kind of throw some of this together. So over here, we're saying f is either increasing or decreasing at an increasing decreasing rate on the interval. So over here for this first part, I'm just saying it's increasing or decreasing. So this is referring to the direction of the graph. And then over here on the second part, notice how we're saying at an increasing, decreasing rate. So the fact that we're saying rate is what's super important. You've got to look for that special word. So when I say we're looking at the rate, that means we're looking at the average rate of change, which of course that means we're looking at the concavity. So if I look from negative infinity to p, the function itself in terms of the direction is increasing. But then if I refer to the concavity, we're concave down, which means it's going to be at a decreasing rate. Now, if I look from P to Q, the function itself in terms of direction is decreasing, and we're concave down, which means it's at a decreasing rate. So we're decreasing at a decreasing rate. Next, we're looking on the interval from Q to R. So Q to R, the direction itself is decreasing, but now we're concave up, which means it's at an increasing rate. So we're decreasing, but at an increasing rate. And then lastly, we're looking on the interval from R to infinity. So in terms of direction, the graph is increasing. And then in terms of concavity, it's concave up, which means the average rate of change is increasing. So we're increasing at an increasing rate. All right, then number 9, we're looking at where it's positive and negative. So I'm just going to take a quick look at my graph. I'm negative from negative infinity until -2, and then from -2 to point C, well, and until 4. I should have done this in a different color. To me, green is positive. There we go. So when I look at my interval here, so we're looking to see whether it's positive or negative. So from the interval from negative infinity to -2, well, that's below the x-axis, so that's going to be negative. And then on the interval from -2 to +4, we're once again below the x-axis, which tells us we're negative. And then that last interval from 4 to infinity, we're above the x-axis, so that tells us we are positive. All right, and then this last little section down here, I would say pause here and try this section on your own. All right, so now we're going to find the interval where f is negative. So this right here, this first little column, where it's positive or negative, this is going to refer to the position. So when I say position, I mean in regards to the x-axis. And then we're looking to see if the average rate of change is positive, so whether it is increasing or decreasing. And over here where it's referring to the average rate of change is increasing or decreasing, this is going to be referring to the concavity. So either concave up or concave down. So to kind of break this apart a little bit more, we're looking for the segment of a graph where it's negative, and then the average rate of change is positive, which means it's going to be increasing. And then when I say it's the average rate of change is decreasing, that tells us it's going to be concave down. So let me actually break this graph up a little bit better. Let's do, actually, let's just not do the colors. I think the colors will make it look a little nutty. Okay, so I want where it's negative, so below the x-axis, and then I want it to be increasing. So where it's increasing, that could be from negative infinity to -2, or from C to 4. So then I need it to be concave down, which means I have to use the interval from negative infinity to -2. Let me put some arrows on here. So this will be from negative infinity to -2. Now we want where it's, so looking at the next one, so now we want where f is negative, the average rate of change is positive, which once again, that means the function itself is going to be increasing. And then the average rate of change is increasing, which means we're going to be concave up. So I want where it's increasing, so that's either negative infinity to negative 2 or c to 4. But if I specifically want the concave up component, that would be this part over here. So I want from c to 4. All right, and next, part f, I want to find the interval where f is negative. The average rate of change is negative. So because the average rate of change is negative, that tells me it's going to be decreasing. And then I want to know where the average rate of change is increasing. So where it's going to be concave up. So I want decreasing but concave up and below the x-axis. So decreasing is specifically from negative 2 to c, but I want specifically where it's concave up. B right here is going to be a point of inflection. So that tells me from B to C, this is really the part that I'm going to focus on. Now, I have had some students, instead of writing B, they'll write 0. Now, I don't typically have an issue with this, but you got to be careful, because what if B is like 0.001? So something like that. It could be something infinitesimally small. You don't know for sure that B is 0, so just write this with a lot of caution. I would just stick to using the letters, since that's how it's labeled, but just depends on the context of the problem. All right, next, now you want to find the interval where f is negative. The average rate of change is negative and decreasing. So negative right here, which tells you that the function should be decreasing, and then the average rate of change itself is decreasing, which means it is concave down. So I want where it's decreasing and concave down. So decreasing from negative 2 to c, but it's concave down from negative 2 only to b. So negative 2 to b. All right, and then last but not least, then we want where f is positive, where the average rate of change is positive and increasing, which that has to be 4 to infinity. Ta-da! That's a great problem. All right, and then with instantaneous rate of change, I'm actually going to just talk about it for a little bit, and then I'm actually going to transition and do a second video on paper where you can see me do the calculator keystrokes. So with instantaneous rate of change, the idea is that we're doing the average rate of change, but we're going to use much smaller intervals. So we want to get as close to that specific value as possible. So for example, if you look at the intervals that we're evaluating, these values are getting closer and closer and closer to 1. Those intervals are getting much smaller. So we're taking the average rate of change over those really tiny intervals to see if that average rate of change is going to get closer and closer to a specific value. So that's going to kind of segue into what we call a limit, but we'll talk about that later on. So I do want to do number 11 with you guys. So we're going to prove that f of x is linear, and if it is linear, determine f of 8 using the average rates of change. So what's going to happen over here? So I'm just going to draw a little example to kind of give you an illustration or a visual. So we're looking at 4. So I'm going to say this is 4. I'm going to say this is 14. And then 24. By no means is this to scale. So what we want to do is we want to find the slope between these points, and we want to see if it's going to be linear. So meaning, if I find the slope from 4 to 14, and I find the slope to be, say, m, I also want to find the slope from 14 to 24, and I want to find that slope. And what we want to determine is, are these slopes equal? And if those slopes are equal, then that means it would be linear. And then if it is linear, that means I can interpolate, and I can actually find f of 8. So this is ultimately what we're finding. Okay, so over here, I want to start by doing the average rate of change from 4 to 14. So I'm going to do average rate of change. I cannot draw an R, everything is fine. So I'm going to do f of 14 minus f of 4. And that's going to be over those inputs, which is 14 minus 4. Now when I plug in the outputs, so that's going to be 26 minus 11 over 14 minus 4, which is just 10. So 26 minus 11, which is 15 over 10, which is going to simplify to 3/2. So I know that the slope over here in pink, I know this is going to be 3/2. Now I want to see if the slope over here in green is also going to be 3/2. So we're going to do the average rate of change again, but over a different interval. So now I'm going to do from 14 to 24. So average rate of change. So I'm going to do f of 24 minus f of 14. And that's going to be over 24 minus 14. Wow, handwriting is beautiful. So my output at 24, which is 41, minus my output at 14, which is 26. And that's going to be over 24 minus 14, which is just 10. So when I do 41 minus 26, use your fingers if you need to, that's going to give you 15 over 10, which simplifies to 3/2. So what this tells us, my average rates of change, they're the same, which that tells me that this is going to be a straight line. So because it is linear in nature, that means I can find f of 8. So I'm going to interpolate. But more specifically, I'm going to use the average rate of change. So there is a way that you can just do this algebraically using like point slope form or even slope intercept form or whatever. But I specifically want to do an average rate of change setup. So meaning I'm going to set up my average rate of change. And I want to find f of 8. So meaning I'm going to do f of 8. And then I'm going to use 4 as my little neighbor. So I'm going to do minus f of 4, and that's going to be over 8 minus 4. Now, based on my setup and what I've already done, I know that my average rate of change in this linear equation, I know that it has to be 3/2. Okay, and then based on the setup, we're going to have f of 8, which is what we want to solve for. And I'm going to do minus the output at 4, which is 11, and that's going to be over 8 minus 4. And then I'm going to solve for f of 8. So I'm going to treat f of 8 kind of like a variable. So when I simplify, so we're going to have 3/2 equals f of 8 minus 11 over 8 minus 4, which is just 4. Now I'm going to treat it like an equation. So I'm going to multiply both sides by 4. So 4 times 3, which is 12, divided by 2, which is just going to give me 6. Nope, don't need that anymore. And then we're going to add 11 to both sides. So I know f of 8 is going to be 17. Ta-da! All right, so don't forget to check out part 2, which is going to be the instantaneous rate of change. I'm going to show you guys some calculator tricks.